I am Dr. Sayantani Chall. Today my topic of discussion is theories of chemical reaction. In my earlier lecture video, I discussed uh, on the basics of the chemical kinetics, what is the rate, definition of rate, molecularity, order, first order reaction, second order reaction, etc. Now we need to know that why a chemical reaction is going on, what is the driving force behind it. So we already have a basic concept about the reaction rate. What is reaction rate? It's nothing but the speed of the reaction. That means how fast or slow a reaction is taking place. So a reaction is dealing with the speed of the react of the particles of the involving molecules. So fast reaction means fast moving particles, and a slow reaction means slow moving particles. Now, there are few factors that are affecting the reaction rates. So, a reaction is proceeding means there is a collision between the reacting molecules. So, the surface area of the solid reactants is a contributing factor in controlling the reaction rate. If the size of the particle is big, then there is a more extent of collision in between them. The second is the concentration of the reactant. If the concentration of the reaction medium is high enough, that means there is a significant number of reacting molecules, so there is a large number of collision compared to a solution where there is a low concentration. And the third one is the temperature. That means for a gaseous reaction, if we enhance the temperature of the reaction, so what will happen? The increase of temperature will affect the speed of the gaseous molecules. That will increase the randomness of the molecule. Therefore, their average kinetic energy will getting increased. So the collision in between them will get more compared to at low temperature. What is happening at low temperature? So in our today's discussion, we will majorly cover two topics. One is the collision theory and another is the transition state theory. These two theories are one of the earlier theories which were proposed by different scientists to explain how the reaction is, what is the driving force behind the reaction is going on. So collision theory was first proposed independently by Max Storrs in 1916 and William Lewis, and they tried to explain how chemical reactions occur and why reaction rate differs for different reactants. That means if we for the same reactants, if we change the condition, the environment of the reaction, then the rate of the reaction will get different. So what are the factors lying them? So they proposed the collision theory. Collision means uh, required at least two molecules, and when they move randomly to and fro, then there is a collision between them. So every reaction requires some minimum amount of energy, that is called the threshold energy, to reach from reactant to the product side. So the molecule is acquiring that minimum amount of energy, which we often termed as activation energy, through the collision. So collision theory tells about some collisions between the particles causing chemical changes, and effective collisions must have enough energy to break pre-existing bonds and to form some new bonds. So the main postulates of this collision theory is collision required at least two reactant molecules to collide with them to form the product. So, if there is a large number of molecules, so there is a large number of collision. Reactant molecules are assumed to be a solid sphere, and due to the collision, kinetic energy of the reactant molecules is getting increased, and the molecule which acquired the energy either equal to or more than activation energy converts to the product. So, whatever I am saying just few minutes back, that through the collision, the reactant molecule is acquiring that minimum threshold energy that is required for a reactant molecule to go to the product side, which we are defining as the activation energy. And the number of collision between the reactant molecule can be increased by increasing the temperature of the reactant. Again, we just said few minutes back that the temperature is a very significant role, has a very significant role in this collision theory. If we increase the temperature, then the randomness of the molecules will get increased, whether it is a gas phase reaction or other. Then there is a more randomness, more collision. So formation of more effective product, and hence we can say that rate of reaction is obviously proportional to the temperature of the system. So if we see this graph, there is a distribution pattern of the number of particles process energy, and this shows that not every molecules of reactant acquire kinetic energy equal to the activation energy. So all the reactant molecules are not converting into the products. Activation energy is the minimum additional energy that is required for effective collision between the molecules, so they may get that threshold energy to become converted from reactant to the product. So this concept can be expressed by using some simple mathematical treatment, where we will consider for a gaseous reaction there is occurring binary collisions between the gas molecules. Let A and B is our reacting molecule, as is showing in the slide. See that A and B is reacting with each other to produce the product. So according to collision theory, the rate of the reaction, that is highlighted in the red color, rate of the reaction is proportional to the number of the collision between A and B. Therefore, according to the rate law, we can say that rate of reaction is proportional to the concentration of A and concentration of B, and number of collision is again proportional to the concentration of the reactants. Therefore, according to the Arrhenius law, we have the rate of reaction presented in equation 1 in the slide, equal to Z into e to the power minus A by RT. Now here Z is called the number of binary collision per unit time, and EA is called the activation energy. Again, according to kinetic theory, the rate of reaction is related with the number of molecules per unit volume. That is, rate is proportional to N into N, or we can say rate is proportional to N square. Therefore, we get rate equal to K into N square. That is in equation number 2. So equation number 1 is that rate of the reaction equal to Z into to the power minus A by RT. That is in terms of number of collision and activation energy coming from the Arrhenius equation. And rate equation 2 is considering the concentration of the reactant molecule. So there are two reactant molecule A and B. Therefore, if the N is the number of molecules participating in the reaction, therefore rate is equal to K into N square. So if we compare the equation 1 and 2, what we can say that K n square equal to Z into e to the power minus A by RT, or K equal to Z e to the power minus A by RT divided by N square. That is equation number 3. Now, from kinetic theory of gases, the value of Z is given by, that is already derived in some other chapter. So, we will here start directly with the equation number 4. No need to derive these values of this expression of Z here. So, the value of Z, Z is number of binary collision per unit time. So Z is equal to 4n square sigma square root over pi RT by m. Here m is the molar mass of the colliding molecule. Sigma is the collision diameter between the two gas molecules. N is the number of molecules per unit volume A and B. So if we put the values of Z from equation 4 into equation 3, what we get, therefore K equal to 4n square sigma square root over pi RT by m into e to the power minus EA by RT divided by n square. So if we simplify it a bit, then we get the equation 5, which is K equal to 4 sigma square root over pi RT by m into to the power minus A by RT. So here K equal to Z into to the power minus A by RT. Therefore, Z equal to 4 sigma square into root over pi RT by m, which is called collision number. So, collision number or collision frequency, what is the definition of this term? This is the number of collision per unit time in per unit volume. If there is involvement of two different type of molecules here, so Z can be represented as Z equal to sigma square into 8 pi RT root over m1 plus m2 divided by m1 m2. So that root over part m1 plus m2 by m1 m2, it is called the reduced mass. It means it requires when the reaction is heterogeneous. It's not that always reaction will happen in homogeneous. So some heteronuclear molecule is getting participated in the reaction. So then we have to consider the last expression for Z. Next we can test these values of Z for some simple reaction. Let's assume the decomposition of hydrogen iodide. The experimental value of the rate constant is 3.5 into 10 to the power minus 7 at 550 Kelvin, whereas the calculated value was observed as K equal to 5.4 into 10 to the power minus 7 at the same temperature. So here the experimental value and calculated value show good similarity between them. But is the collision theory is not good enough to explain all the types of reactions. Say in polymerization of ethene, there is a large difference between the observed and theoretical values of K. Again, polymerization of 1,3-butadiene, it occurs at rate which is slower of 10 to the power minus 4 times than the theoretical value, and there are many chain reactions proceed with much higher rate than the proposed theoretical value. So, for example, there is a reaction between hydrogen and bromine forming HBr, but what is observed that the reaction is occurring at a much faster rate compared to the calculated value. So, what is the reason behind this? The probable reason may be we said that there is a collision occurring between the gas molecules, between the reacting molecules, but when the molecules is getting colliding with each other, there is a numerous orientations of the molecule. So not every orientation are effective enough for exchanging the energy between them through the collision, but only few collisions are effective with a perfect orientation, which are responsible for the exchange of their energy or help molecule to get the that minimum threshold energy. So here in this slide, I'm showing you schematically that the collision posture must be effective. The collision orientation in during the time of collision, the orientation of the molecule must be perfect, so that the molecules would be able to get that required minimum energy to reach to the product side. Therefore, we are introducing here another factor that is called the polarized orientation factor. It is represented here as P. So in the modified equation, therefore, for the rate expression for the rate constant is K equal to P into Z into e to the power minus A by RT. That P into Z, this two parameter combinedly can be compared as the Arrhenius equation A factor, which is called the P exponential factor. So the values of P theoretically can be between 0 to 1, and practically it was observed between 1 to 10 to the power minus 8. So up to this is some basic discussions of collision theory. But even after the correction of this orientation factor, the collision theory is good enough for explaining mostly the gaseous reactions. But there are many solid phase reaction, solution phase reaction. But this theory is not good enough to explain all that theory. So some advanced theory is there, which is called the transition state theory, is proposed by Henry Eyring at 1935. So in transition state theory, it introduced the concept of mainly transition state, activation complex, and reaction intermediate. So according to the transition state theory, we can say that a state where molecules are the reactants and the state where the molecules are products, there is a state known as the transition state, and in transition state a complex is formed by the reactant molecules to which is called activated complex. So in this theory, three major factors determining actually the reaction. One is the concentration of the activated complex, another is the rate at which the activated complex breaks apart, and whether it breaks apart to reform the reactant or it breaks apart to form a new complex with the products. So, I am repeating here, the factors are the concentration of the activated complex, another is the rate at which activated complex breaks, and when it breaks, whether it converts to the reactants again or it forms some new products. So this is a simple potential energy diagram where the reactants A plus B producing the product P plus Q passing through some energy minima, which passing through some high energy state, which is called the activation state. And at that high energy state, say, see there is a representation X dagger. This is called dagger, is formed, which is called activation complex. And this activation complex consisting of a bond which is two bonds. One is a weak bond and another is a new bond. One is an old bond, another is a new bond. Then both the bonds are weak here, and the energy gap and the energy gap from the reactant molecule to this high energy state is called the energy of activation, which is required to attain this transition state. So if we if we give an example, very common example, SN2 reaction. SN2 reaction is a very good example to understand the transition state theory. So if we consider the reaction of methyl bromide with OH minus, that is a hydroxyl ion. Here OH minus is acting as a nucleophile. So in SN2 reaction, what is happening there? In the transition state, there is a formation of an activated complex where there is a new bond formed between the methyl carbon and the bromine, and there is a along the bond distance. Sorry, there is a new bond formation between the methyl carbon and oxygen, and the old bond C-Br is going to break. So the C-Br bond is getting more weak and a new CO bond is forming here in the transition state, and the amount of energy required to form this complex is called the activation energy. And after passing through this formation of this activation complex, that transition state complex is giving rise to the new product of methanol and the bromide ion. So in summary, we are showing here that the OH minus is attacking from the OH minus is attacking from the backside, and therefore in the transition state, that brown color ball here is indicating the bromide ion, and the blue color bond is indicating the oxygen, and red ball is indicating hydrogen, the black ball is indicating carbon. So there is initially no bond between the blue and black ball, that is the carbon and oxygen, but there is a bond between carbon and bromine, blue ball, and the violet ball. But at the transition state, there is a new bond forming between carbon and oxygen, and there is a the bond between C and Br, the black ball and the brown and the purple colored ball is getting weak. And finally, at the last stage, there is a formation of methanol, a strong bond between carbon and oxygen, and the bromide ion is getting weak. So activated complex is clearly different than the reactants and the products, and a successful collision and reaction should be occurred so that we can get finally the desired product. So by using these two theories, we can primarily explain, or we can understand that how the reaction is going on. We know that there some activation energy is required, but by studying this mechanism, by studying these theories, we can able to understand that by which the molecules acquiring that amount of energy to passing through that energy pathway, to passing through that activation complexes or activation energy to form the final product. Thank you.